To start Adam's fantastic talk. So to start with, Adam completed a PhD in artificial intelligence at UC Berkeley and is now the CEO of a fantastic organization called FAR AI. He's going to be giving an exciting talk on AI safety and is welcoming many, many questions at the end. So I'm going to let him take over now.
I hope I can live up to the introduction. So I'm Adam, and today I'm going to be trying to give a summary of the landscape of technical AI safety research agendas. So recently there's just been this proliferation of new research agendas and organizations seeking to pursue those agendas. So Stephen McAlsey estimated in the last 2 years alone, the number of organizations working on AI safety has doubled. Now this is very exciting to be part of such a rapidly growing field, but it does mean that it's quite challenging sometimes to keep track of all these different organizations, what agendas they're pursuing, and why. In this session, I'm going to be giving a summary of the landscape of the most popular current AI safety agendas. So my hope is that by the end of this talk, if you're talking to an AI safety researcher or reading a paper, you'll have the context to understand how what they're working on fits into the bigger picture of AI alignment, why they're excited by it, and what the main arguments for and against that agenda are. There are going to be several very important topics, but I'm just not going to talk about at all in this talk in the interest of time. So firstly, I'm not going to be really talking about why AI safety matters or how we should be prioritizing it relative to other cause areas. There's a lot of excellent resources that have covered this in more detail than I'd be able to. I've listed some of my favorite ones here, but this is not to say it's not important. We're just not going to be talking about it today. It's also important to recognize AI safety is not purely a technical problem. In fact, if we could just all coordinate to not build really advanced AI systems before we know how to make sure they're safe and reliable, then that would basically solve AI safety. Now, that's a very challenging governance problem, but just more generally, I think we can really make a lot of progress on the governance side, which will make it easier to satisfy the technical solutions. If we have good incentives for major AI labs, they're going to solve some of the safety problems without necessarily us having a dedicated safety community. So the governance work, really important. Some organizations in the space to check out if you're interested would be GovAI and the Center for Study of Emerging Technologies, or CSET. Finally, there's this kind of philosophical component to alignment. So suppose we do solve alignment. That's great. But what value should we align an AI system to? And how should those values evolve over time? We don't want to just lock in 21st century values. That would be bad. So there's some deeper philosophical issues that I don't think we currently have a satisfactory answer to. Some good organizations in this space would be the Future of Humanity Institute at Oxford, and more recently the Center for AI Safety, or CASE, has hosted a philosophy fellowship trying to train new people in this area. So even just narrowing down to technical research directions, there's still a really wide range of research agendas that people are working on. And I think it can be kind of a bit surprising, especially if you're used to other more established research fields where there's a few dominant paradigms. One thing I think is important to recognize is that in many ways, AI safety is more a problem that we're trying to solve rather than a research field itself. So when I say research field, I think of a community of researchers who publish in the same venue, have a shared epistemic standard, and are kind of using a common methodology. So this could be something like natural language processing, artificial intelligence. People publish in EM/NLP. They have agreed to kind of measure progress by certain benchmarks like superglue. And then you have problems that are like real-world issues that exist whether or not researchers were studying them. And a variety of researchers from different disciplines might be trying to tackle them. So an example of this might be climate change, which has contributions from climate scientists, electrical engineers, material scientists, just a really wide range of disciplines. Technical AI safety, I'd say, has some parts of both. It is more concentrated on artificial intelligence research, as the name would suggest, than something like climate change is. So in some sense, it is closer to being a research field. There's also some common publication venues, like the Alignment Forum. But for the most part, I'd say that, AI safety is more a problem. There's not a single research methodology that can solve it. So in that sense, it's kind of not surprising that such a complex and multifaceted issue would just have a really broad range of agendas. Given such wide variety of agendas, it's useful to have some kind of taxonomy to categorize them and help make sense of what otherwise just be this overwhelming list of different approaches. One breakdown I think is useful is to think what methodology is a particular agenda using. Is it conceptual, theoretical, or empirical? Empirical research is probably the easiest to understand, where you're trying to study contemporary AI systems, either to understand the capabilities and risks that they and future AI systems pose, or to test a particular alignment idea, see if it makes systems safer. There's also theoretical work that is more about studying a particular idealized model of an AI system and trying to derive properties that you can prove about that idealized model. Finally, there's more conceptual work, which is in many ways closer to philosophy. So this might look more like an informal discussion about what we might expect AI to progress in the future based on historical trends, based on intuitions about intelligent systems. In practice, I think that many of the best research is a blend of all three of these, but people do tend to specialize in one area over the other, and many organizations pursue primarily one and the other. You'll see a lot of people just lump the last two categories, sort of mathematical theory and conceptual work, as like one thing, theoretical work versus applied work where you're actually coding. That makes some sense, but I think the epistemic standards of theory work and conceptual work are really quite different. One of them is rigorous math, the other is kind of you write a Google Doc and share it with your friends. So in that sense, I think it makes sense to break down the two. Another kind of major driver of differences can be that people just have different beliefs about how AI safety, how advanced AI systems are going to be developed, and what implications that has for safety. In particular, people's timelines for when transformative AI will be developed just vary by an order of magnitude. So there are people in this community who think that there's a 50% chance in 5 years' time we'll have an AI system that transforms the world. And there are people who think, no, it's going to be decades away, or maybe it will happen sometime in our lifetimes or our children's lifetimes. We don't know when. And you're just going to pursue a radically different strategy depending on if you think by the time you finish a PhD that you might be starting, transformative AI will already be here, versus you thinking you've got several decades to work on it. Another major difference is what techniques we think are going to be used to develop advanced AI systems. One possibility is that they look very similar to today. This is kind of prosaic machine learning. So this might look like you just take a neural network, you make it bigger, you train it for longer, it gets better. This is basically the bet that OpenAI is making. And so far, it's worked pretty well the last few years. But there's other beliefs. So DeepMind, for example, is pursuing, or at least has been pursuing historically, something that looks more like finding many different kinds of algorithmic insight to get small progress in AI and then trying to bring them together. So this might look more like being inspired by the brain and having many different cognitive modules and then putting them all together. And this is something where, we might be more bottlenecked by insights, it might be more unpredictable, we might have more modularity. And then there's also a possibility of something just completely left field that we're not currently considering. Probabilistic programming languages might be one example of this. I think it's worth having some humility because in the history of AI, people have changed their mind at least 3 times about what the prominent paradigm is. And if you look back a couple of decades, people are getting very, very excited about things like expert systems and thinking that was about to kind of transform the world. And it didn't happen. Now, that's not to say that that's going to happen this time. I think there really are some major differences here. Deep learning is seeing commercial traction, but we should sort of expect that we might still see a major paradigm shift. Finally, there's this kind of major disagreement sometimes about just how difficult the problem is. So on the one hand, you might think, basically, we're going to have alignment by default. That just in the usual course of affairs, no one designing ML systems wants to die, or even just wants it to do something that's toxic or undesirable. So people are going to catch these errors and fix them. And then there's another belief that maybe thinks these problems are going to be very subtle, that we might only have one chance to get them right. And suddenly, software engineering as a discipline is not known for shipping bug-free software on the first try. So, if that's the situation we live in, then it could be a very difficult problem to solve. Finally, I think you can break down research into the different stages. So early stage research tends to focus on idea development. This would look a bit like Albert Einstein coming up with general relativity in 1916. But there's also this important step of validation. So in the case of general relativity, 3 years later, Arthur Eddington empirically tested general relativity by measuring light deflection during a solar eclipse. And even once you validated it, you still need to actually apply this to practice. And in the case of general relativity, that took almost 5 decades for the first kind of commercial application of it in the form of global positioning system satellite. And the interesting thing is that when the Air Force contractors were designing the global positioning system, there was actually significant disagreement in the team as to the magnitude of relativistic correction needed, and even the sign of a relativistic correction. There were a few people on the team that thought that no relativistic correction was needed at all, and were somewhat doubtful about general relativity. So this disagreement was only resolved after they launched the test satellite, NST-2. And it did validate that general relativity was correct, but found several mistakes in the calculation of the engineering team because they hadn't applied general relativity correctly to that problem. So I think this is kind of illustrative that there can be this quite big gap between just having a well-established, validated scientific theory and people knowing how to actually apply it in practice to a problem. So generally, I think when we think of research, we think of this first stage. Probably everyone has heard of Albert Einstein. I'm guessing most people have not heard of Arthur Eddington. I certainly hadn't before, until relatively recently. But this second step of validation is really key to actually getting people to take alignment ideas seriously and also make sure that we're on the right track, that we really have solved the problem. And then there can also be a lot of important work to done in translating these ideas into practice. All right, so with that, let's actually look at some concrete alignment proposals. A key problem in AI safety is value alignment, so teaching AI systems what our values are and incentivizing them to pursue those values. In the case of large language models, a popular approach to alignment is called reinforcement learning from human feedback. And the idea is you start with this unsupervised learning trained model, so you just train it to imitate text on the internet. And then you fine-tune it, so you keep on training it with reinforcement learning to maximize the reward generated by a model trained on human feedback. So basically, you're trying to make it do things that humans would approve of and not do things that humans wouldn't approve of. This is a pretty mature approach at this point, so it's been applied in settings such as InstructGPT and ChatGPT from OpenAI, as well as Anthropic's paper, Helpful and Harmless Language Models. However, a lot of people are kind of skeptical of it because it's really just a shallow approach to alignment, as it were. So it's strongest if you believe alignment is relatively simple, going back to the alignment difficulty axis, and if you think that we have maybe relatively short timelines, so we don't kind of have time to try something more sophisticated. One concern people have is that it can only really work in situations where we're able to provide high-quality human feedback. And in fact, this has been a major problem in practice, that if you just get crowdsourced workers on the internet, they're often going to take shortcuts and train the model in the wrong way. But even if you had kind of the highest caliber model, we get Nobel Prize winners during the data generation, there's still going to be some situations where humans just don't know the correct answer. For example, there's wide disagreement about what the right economic policy for a country might be, and we'd like to apply AI systems in contexts where they are more capable than us and trust them to be able to do the right thing even in situations we can't judge. So this is the idea behind scalable oversight, where you want to train an AI system to be able to evaluate situations that we're unable to do ourselves. One proposal for this was by Paul Cristiano called iterated distillation and amplification. The idea is you start with this imitation-learned model of a human, so it just does exactly what you would do in any given situation. And then you amplify it to make it more capable than you by allowing it to ask recursive queries to copies of itself. So it's like you've suddenly got a bunch of clones of yourself that you can delegate some tasks to. And then they come back, and you get their answer from your clones, your copies of yourself, and you make a decision based on these reports. So that's the amplification step, where it's kind of like you've been able to think for longer than you usually would. And then you distill the results of this amplification process back into the model, because if you just kept amplifying it, it would kind of be computationally intractable. You'd have tens of thousands of copies of this model. So you try and make it predict the output of this amplification. And then you repeat this, and the hope is that at the end of it, you'd end up with a model that is doing something similar to a society deliberating deeply on a problem, but is able to return an answer in a reasonable period of time rather than waiting 100 years for a deliberation process to complete. As you might have guessed from that description, a lot of the work in scalable oversight is more conceptual rather than something people can actually implement. But there are some proposals that are a little more down to earth. One example would be Jan Leiker of OpenAI had an agenda recursive reward modeling, where the idea is you train an AI system to help evaluate the output of other AI systems. So if you want a system to summarize a book, you might train a system that tells you whether a particular output is grammatically correct, have another system that does fact-checking. And then this makes it much easier for you to test whether some summary of a book was correct without having to read the entire book yourself. And there's also approaches like AI safety via debate, which is by Jeffrey Irving, where you have two AI systems debate one another, and the hope is that it's easier for a human to judge the output of a debate than just test whether a single AI system's output is correct, because you can't hear the counter-arguments to it. So generally, scalable oversight seems most promising if you think that alignment is relatively hard, so simpler techniques like RLHF just won't work well enough. It's also relies on us having sort of long enough timelines that we actually can make some progress on this, because it's not exactly an idea that's ready for application right now. And generally, people are viewed as being kind of closer to tackling the harder of alignment problem, but maybe not something that we actually need to solve. So that's kind of a more controversial part. Even if we are in a situation where humans can provide reliable feedback, there's widespread disagreement about whether existing reward learning algorithms are going to be sufficient to accurately capture human preferences. So this could be a problem even with vanilla RLHF in situations that humans are capable of judging. Much of the work in this area has leaned towards being more theoretical in nature. For example, Dylan Hadfield-Manel's paper, Cooperative Inverse Reinforcement Learning, also known as assistance games, formulated value learning as this cooperative game between a human and a robot. And the idea is that the human knows what their values are, the robot doesn't, but the robot wants to maximize human values. There's also been more applied work in this domain. For example, Dorsa Sadiq's lab at Stanford has done a lot of work on active learning, seeking to make reward learning more sample efficient, because currently it takes things like 5 years of full-time equivalent labor to teach a model how to summarize an article correctly. That's not terrible, but it's like a pretty simple task. So if you're trying to scale it up to more complex tasks, that might not be practical. Active learning might be able to make this much more scalable. The general reception of reward learning has been that it does provide important conceptual clarity to the problem, but there's skepticism as to whether the approaches people have developed so far are really practically applicable. For example, cooperative inverse reinforcement learning has been implemented in domains with as many as 4 states. I don't think anyone's managed to make it work in 5 states. You probably could if you worked hard enough on it, but unfortunately the real world has a lot more different states than 5, from number you can count on one hand. On the active learning side, that tends to make assumptions that are somewhat unrealistic, relies on a lot of Bayesian reward learning techniques, but we just don't currently know how to implement at scale. I think reward learning looks most promising if you believe that existing methods for value learning are going to fail to accurately reflect human preferences. For example, because they make unrealistic assumptions about humans, in which case we might just need fundamental progress. Many problems in AI safety can ultimately be traced to failures to generalize correctly. So if we think of scalable oversight in a way that's trying to make a system generalize from situations that we're able to judge to those that we're unable to judge, but still do the thing that we want. So given that there's so many things are pointing in the direction of generalization, it can make sense to focus specifically on making models generalize well. In particular, we'd like AI systems to generalize in the same way we do. One proposal for this from Paul Cristiano, again, is called imitative generalization, where the idea is you directly learn how a human would generalize in a novel situation by seeing lots of examples of a human being effectively exposed to a novel context, and then seeing how a human responds given that situation. Like a lot of Paul's proposals, this is more conceptual rather than something you can actually implement. But there has been some work gaining conceptual clarity here. For example, follow-up work from the Alignment Research Center on eliciting latent knowledge, or ELK, as you often hear people call it affectionately, is sort of formally specifying this problem of how do you make an AI system generalize to actually do the thing you intended, rather than just kind of learn a perfect simulation of you that copies all of your flaws, all of your limitations. On the flip side, there's a number of people who believe this problem basically just doesn't exist. Which kind of reflects the widespread disagreement in AI safety about research prioritization. So one example would be John Wentworth. He's working on this natural abstraction hypothesis, where the idea is that perhaps there's just a small set of reasonable representations that any intelligent system trying to make predictions about the world would learn. For example, it might just be that if you're trying to classify images in the world, learning a concept like tree or table is just useful because these are objects that occur. And perhaps if we have those concepts, so will AI systems, so would aliens who land on Earth tomorrow. In this case, generalization just might happen without any additional work because we will share the same concepts as an AI system. There's also a lot of work kind of in the middle that isn't aiming to have perfect copies of human generalization, but is trying to improve generalization relative to contemporary techniques. For example, Aligned AI, which is this Oxford-based nonprofit, is developing techniques to ask users when there's ambiguity in the data, when there's multiple conflicting explanations for the data, and then hone in on an explanation via that. There's also a huge amount of work in academia on generalization, although how much is relevant to safety varies quite widely. Generalization is concerned with trying to get good average case performance on a different distribution. But sometimes we actually want something a little bit different, which is a worst case guarantee. So no matter what situation we find ourselves in, we might want an AI system not to take a certain catastrophic action. This is naturally framed as being an adversarial robustness guarantee. So if I'm trying to break your system, I'm trying to make it do the wrong thing, can you give me a guarantee that no matter what I do, your system is not going to fail in a certain way? There's just been a huge amount of work on adversarial robustness in academia, but unfortunately a lot of it has focused on what I and many others would consider to be a slightly restricted setting. So if you're come across AI, you've quite probably seen something like an adversarial example where you take a clean image of, let's say, a cat, you add these barely visually perceptible perturbations to the image. To a human, it looks exactly the same, and an AI system now thinks your cat is a dishwasher or whatever target you wanted it to be. And people have been working on solving this problem for the best part of a decade, and there has been progress, but basically it's still unsolved. You can still exploit state-of-the-art models by adding, we've gone from completely imperceptible perturbations to if you squint at the image really closely, you can see something's got to happen to it. But you can still totally fool these models. So this is a little bit concerning, perhaps. We've not been able to solve this. And unfortunately, when used, kind of gets worse, because if you consider more realistic threat models, then the attacker can just do more and more things. So for example, Justin Gilmer of Google Brain had this paper motivating the rules of a game for adversarial examples, that outlined a wide range of different things that attackers could do, and why this might or might not be realistic. I'm particularly fond of Tom Brown and others' framing of unrestricted adversarial examples, where we really just say, look, you can give a image classifier or other model any input you like, and it has to get the right answer if a human would be able to classify it correctly and unambiguously. So basically, can you replicate human robustness? And that's a problem that we're very, very far from being able to solve, unfortunately. Another threat model that I and some others at FARIA have been pursuing is adversarial policies. And here the idea is you have a multi-agent environment, so this could be something like a board game, and you have a defender agent and an attacker that's trying to exploit this defender. And the key thing is that this is a symmetric game, so there's nothing that the attacker can do that's special that the defender can't do. It just has to find some strategic weakness in the defender. And what we found is that even superhuman systems, so even things like CataGo, which is this open source Go playing system, it can beat top human professionals. even these are very vulnerable to adversarial policies, would do something that is completely crazy, would not win against a human. And so this is really showing these systems have learned very kind of non-robust heuristics, even if they work quite well in the common case. Finally, there's a substantial literature attempting to understand why adversarial examples exist, kind of like why has it been so hard for us to get rid of these? And I think good examples would be Alexander Madry's lab, with papers such as robustness may be at odds with accuracy, or adversarial examples are features, not bugs, which is trying to argue this is a really fundamental problem that you can't get rid of without hurting kind of accuracy in the common case. In terms of like whether this is a promising agenda or not, it generally looks strongest if you expect transformative AI to be prosaic, to look similar to contemporary systems. If you think it's going to be a completely different technique, then it's just very likely that we're going to have to redo most of this work with a new paradigm. Within the safety community, I think there's some people believe that adversarial robustness is likely to be solved by default. So if you just have a sufficiently capable system, kind of surely by virtue of it being really intelligent, it's not going to fall for these stupid adversarial examples. Unfortunately, kind of so far, we've not seen that just more capable systems necessarily do become adequately robust. They do become a bit harder to exploit, but the trend isn't really strong. So this is still somewhat of an open question. A kind of special case of adversarial robustness would be Mesa optimization, although the story behind it is quite different. So the idea of Mesa optimization is that a system might learn an inner objective that is different to the objective that you trained it with. And in some ways, humans are Mesa optimizers for evolution. So we were, informally speaking, optimized by evolution, by natural selection, to maximize our reproductive fitness. But I don't think most of us go around thinking, like, how do we maximize the number of offspring we have? In fact, we do a bunch of things that are like really counterproductive to reproductive fitness, like we love eating sugary food, which just harms our health. Now, many of these things made complete sense to do most of the time in the evolutionary environment. When calories were scarce, eating sugary food is a great idea. And you might expect something similar to happen with AI systems, where they learn objectives that are correlated with a true objective, with an outer objective at training time. But when the situation changes, they're just going to continue to keep on pursuing these internal objectives they've learned quite capably, even if this is now counterproductive to the thing that we were trying to train them to do. Most work on Mesa optimization is conceptual in nature. One of her original papers was from Evan Hubinger, Risks from Learned Optimization, that attempted to formalize Mesa optimization as being this planning process with an internal objective. And there's also been a limited amount of theoretical and empirical work on the problem. For example, minimal circuits, which is this sort of formalism of an idealized training process, have been shown to tend to result in planning procedures, which might suggest that Mesa optimization is likely to occur. There's also been some empirical demonstrations. So Jack Koch and Laura Lungosko in recent work showed that a reinforcement learning agent that was trained to collect a coin instead learned just to kind of go to the rightmost part of a level, which is where the coin happened to spawn during training time. Overall, I'd say that Mesa optimization is probably one of the most controversial agendas in AI alignment. Some people think it is the core problem in AI safety. If we don't solve this, it's not going to work. You're going to get deceptively aligned systems. They look like they're doing the right thing, but we're actually, pursuing these inner objectives and just pretending to be aligned because that helps them pursue those inner objectives. And there's other people who say, like, look, this is just a completely, speculative problem. There's no empirical demonstration of it. The theoretical arguments are really sketchy. We don't need to worry about this. I'm kind of hoping that in the future we do some science on it and figure out which one of these perspectives is true. But right now there's pretty widespread disagreement. There's also a reasonable fraction of people who are concerned about this problem but think that Mesa optimization is not the right framing for it. For example, Rohan Shah of DeepMind, he prefers an alternative frame that looks a little bit more like generalization, although it's talking about the same basic problems. So far, we've been talking about how do we make an AI system be more aligned, be safer. But the flip side of this is how do we know if an AI system is safe? One approach is to study the contemporary behavior of AI systems and try to learn more about the capabilities and risks they pose and test whether alignment of techniques make them safer or not. This is often known as black box evaluation because we're effectively taking an AI system and treating it as this opaque black box where we can't stare into the internals of it at all. Black box evaluation is naturally empirical in nature and tends to be focused on validating systems. A key assumption is that safety-relevant properties of a system are able to be tested by looking at the behavior of a system. This is controversial for kind of the same reason that Maser optimization could be a risk. If a system is deceptively aligned, it might just pretend to do really well when it knows that you're testing it, but is going to, basically do a treacherous turn when it knows that it's free to do so. And this, humans do this, right? If you're interviewing someone, they might be trying to fool you. So this is a major limitation of it. But you might hope that at least at certain stages, systems aren't going to be able to do this, and you are able to evaluate systems for kind of their entire training history. So this gives you some benefits. One example of this kind of black box evaluation would be benchmarks for value learning. For example, the Basalt benchmark by Rohan Shah, Cody Wild, and others is a benchmark in Minecraft where you have natural language descriptions of tasks, like build a house in the style of existing houses in this village. Now, for a human, that's a pretty kind of clear, simple task description, but it's very hard to actually procedurally specify. And this is empirically proved to be a pretty challenging problem for people to solve. Another approach is to develop new empirical methodologies to test particular alignment-relevant problems. For example, with scalable oversight, we have this issue where what we want to test is whether systems that are too complex for any human to judge or evaluated correctly by an AI system. That's a little hard to test because we don't have any ground truth labels. By definition, we can't test whether it's doing the right thing or not. But what we can do is we can take humans that are non-experts and don't know what the right outcome is, train a model on this non-expert feedback, and then evaluate the model's output with experts who do know the right answer. So this might look like some people who are just lay people trying to fine-tune a language model to be a useful health advisor, and then having doctors come in and test whether it actually is more useful than an original model. This was proposed by Ajay Kocher of Open Philanthropy, and recently a team led by Sam Bauman have applied this approach to question answering benchmarks in large-scale language models. In addition to validating the alignment proposals, black box evaluation can be used to better understand the capabilities and risks of AI systems. For example, a team at Far AI, led by Ian McKenzie, developed the inverse scaling approach, where the idea is to pick problems where as you make the model bigger, as you train it for longer, with more compute, more data, performance actually gets worse. And this is rare. Most of the time when a model gets bigger, it does better. But if you do have a problem that exhibits inverse scaling, then this isn't a problem that's going to go away in the default course of affairs, so you're going to need a dedicated safety effort to resolve it. Another example would be the Alignment Research Center's evaluations team, led by Beth Barnes, is looking at doing kind of gain-of-function research in AI systems. So taking an AI system and saying, can they make it do something that would be concerning, that would be kind of a warning sign. So an example might be you take a language model and you train it to be deceptive, and if it's really good at deceiving you, then you can say, well, we know these models have the capability to deceive us, we should be aware that there's a risk they are actually doing this when we don't train them to be deceptive on purpose. We might still learn to do that. The flip side of black box evaluation is kind of white box evaluation, specifically mechanistic interpretability, where you try and understand the inner workings of a model in a large amount of detail. And if you could manage to do this, this would be really useful because you can then make predictions on how the model is going to generalize, whether it's going to be adversarial or robust, whether it has the same representations that we do. Generally, mechanistic interpretability, I think everyone agrees, if it worked, would be really, really great. And because there's a lot of excitement about mechanistic interpretability, but there's also a decent amount of skepticism of whether it's tractable, right? You know, we need to understand maybe trillion parameter language models. We're almost there. That's a lot of parameters. If I just give you a 1,000 coefficient linear regression, that's already pretty difficult to understand. So kind of, can we really develop techniques that are going to be able to let us understand things at a really sort of fine-grained level, especially for AI systems that weren't necessarily trained to be modular or interpretable. So I think basically everyone agrees it would be good if it worked, but there's a lot of disagreement about tractability. In terms of actual research, A lot of early work on mechanistic interpretability focused on image classifiers. So Chris Oler's Building Blocks of Interpretability is a good example of this. Recently, there's been this kind of really big pivot towards language models, but and every other aspect of safety pretty much. And so Chris Oler's team at Anthropic is now focused on understanding particular circuits in language models. And similar work coming out of Redwood identified particular circuits doing things like copying, summarization. And there's also a kind of really wide range of other methods that have been developed that are at varying levels of completion. Finally, there's a few agendas that just don't really fit into any other section, which I'd be, I think, remiss not to mention at least once. One is multi-agent alignment. So far, everything we've spoken about has been how to make a single AI system do the right thing. That's important, but we already have many AI systems deployed in the world. In many cases, they're going to be interacting with one another. By the time we have transformative AI deployed, there's probably going to be a really large number of AI systems in the world. And as soon as you develop transformative AI, the first thing you're going to want to do is copy it, run it in many different places. So we really need to make sure that the aggregate output of these AI systems is aligned, not just the output of any single AI system. And this might be quite challenging because for the most part, I'd say humans are trying to do the right thing. Maybe they have slightly different values, but most humans are not psychopaths. And yet we have all these problems that are down to coordination failures. Like it's hard to produce clean air because lots of people in isolation would rather pollute a little bit more of a margin. So we often fail to produce public goods. You also have issues where conflict arises, right? People don't have the same values. Well, AI systems trained by different companies in different nations probably won't have exactly the same values either, even if they're aligned to kind of the company that they're being designed by. Even if we're, let's be optimistic, aligned to a democratically elected nation state or large population of the world, there's still going to be different assumptions, different alignment techniques. So these AI systems could come into conflict with one another and cause many of the problems we see today. Now, to some extent, this isn't a new problem, so maybe it's less scary. But this is a problem that could happen at large scale and quite rapidly, which existing human institutions for conflict resolution, for coordination, might be unable to handle. So this is, I'd say, a relatively kind of early stage research field, although there is a wealth of related work in other academic disciplines like game theory, social choice theory, multi-agent reinforcement learning. One research agenda in this area is Andrew Critch and David Kruger's Arches agenda. That has a sort of really wide range of different directions. More concretely, Alan Defoe and others have suggested the cooperative AI agenda, trying to train AI systems to be able to cooperate with each other and help humans cooperate with one another as well. This is being pursued by the Cooperative AI Foundation and also by Vince Collins's lab Focal at Carnegie Mellon University. I'd say the reception of this multi-agent work has been pretty mixed. I feel like I've been saying that for many of these agendas, but maybe this is particularly true for multi-agent. On the one hand, it could be a very neglected direction because no one's really directly incentivized to fix it, right? No one wants to build an AI system that does something that they don't want it to do, but perhaps people are okay with AI systems doing something that are more like pollution, that have negative externalities. But the flip side of it is that it's not clear what we can do that future aligned AI systems wouldn't be able to do to solve this problem. So if I have an AI system that's trying to help me, and it can see that my values won't be satisfied because of some coordination failure, then it should be motivated to go away and do this cooperative AI research and convince all the other AI systems to adopt it. So, maybe there's just nothing that we can do and we should just sort of outsource it to future AI systems. I've often referred to AI agents in this talk, but this notion can actually be quite hard to formally pin down. Agent Foundations is an agenda pioneered by the Machine Intelligence Research Institute, and the idea is formally characterizing notions of agency and related properties like optimization. This would be useful both to gain conceptual clarity and also as a source of information about future AI systems. Ultimately, we can prove something for arbitrary agents, and we know it must hold for AI systems no matter how they're developed. So this is particularly useful if you believe that prosaic machine learning is unlikely and we may have radically different techniques in the future. Work on agent foundations is primarily conceptual and theoretical, Although the agenda is one of the earliest in AI safety, I'd say it's still fairly early stage because it's just a really ambitious research problem, so we've not made kind of that much progress on it. Some examples of it would be Nate Soares and Benji Afalazzine's research agenda, Agent Foundations for Aligning Machine Intelligence, and more recent work would include Scott Garabant's work on Cartesian frames and Vanessa Koso's work on infrabayesianism. Reception to Agent Foundations has been pretty varied. I think everyone thinks it's going to be like positive if it succeeds, but there's kind of pretty wide disagreement as to whether we need it to succeed and so how tractable the direction is. Sahil has a whole talk dedicated to this topic at 5 p.m. today, so if you're interested in learning more about it, then I suggest checking out that talk. Finally, there's important to recognize that aligning an AI system to human values is not purely an AI problem. It also depends a lot on human psychology, cognitive science, how we interact with those AI systems. So there's kind of two ways, I'd say, that cognitive science and related disciplines can contribute. One is by better understanding human intelligence, because that's kind of the only extant general intelligence we have, so we might be able to learn something about how AI systems will operate from better understanding human psychology. The other side of the coin is that we would like to better understand the limitations of humans so that we can model that accurately when we're trying to learn human preferences. So one important category of this work would be human and robot interaction. For example, Anka Drugan's lab have studied mismatch between AI systems' model of humans and how humans actually behave, how this could lead to AI systems learning the wrong objective, and how we could correct that by having more accurate models. I think there's also a number of kind of forecasting questions that are relied on information about the human brain. For example, Joseph Carlsmith's report for Open Philanthropy looked at how much computational power it would take to simulate the brain, and this is being used as a sort of biological anchor for how long it might take us to develop AI, because probably the brain's pretty compute efficient, so we don't have enough power to simulate a brain. We probably won't be able to get sort of human-level AI. There's also kind of a possibility that advanced AI systems might be developed that are very inspired by the brain, that are more neuromorphic, rather than just scale-up versions of contemporary ML systems. So Steve Burns, in an introduction to brain-like AGI safety, outlines a variety of research directions relevant for neuromorphic transformative AI. This was a brief overview of current safety research directions. I've included a copy of the slides on this link. It also includes a bibliography of all the papers I mentioned, because I'm not expecting everyone to remember 40+ papers. Although I've attempted to be objective in this talk, ultimately this was necessarily colored by the areas I'm most familiar with and my kind of personal biases and what I'm most excited about in this area. So I'd very much encourage people to view this as kind of an initial stepping stone towards understanding the landscape, but also look at other people's taxonomies, other people's arguments for and against directions. Ultimately, AI safety is a pretty early stage field, and this is really exciting because you've got a lot of opportunities you just wouldn't have in something like maths or theoretical physics research where the question's already really well studied. But the downside is you do have to do more work yourself to figure out what the right problems to work on are. So kind of developing that research taste is really important, and I think everyone should approach that with their own perspective and not just defer to people like me just because I've been in the field a few years more than you. All right, well, thanks, and I'd love to take questions, pushback, disagreement, conflict.
Thank you for that great talk. Someone who has zero background in AI safety, I learned a lot, and to be honest, it was very easy to understand, and I didn't think I would learn this much. So if anyone has any questions to ask, can I ask everyone to use their Swapcard app, go into the talk, and there's a live discussion button you can use to chat a question or put it into the questions poll, and then I'll have it to ask Adam right here, and then he'll answer your questions ASAP. He's very kindly left a few extra minutes for the questions, and hopefully we hear a lot. If not, I have a lot of questions myself. There's already a few questions in there, Adam, so I'm going to start. Distant is it to have a concrete beliefs on AGI timelines in choosing a research sub-area to work on. How much have timelines guided the problems you pick compared to interest and tractability?
Sure, thanks. It's a great question. I'd say that having a coarse-grained view of timelines is pretty relevant. Like if you think that it's 5 years versus 20 years, that's probably going to make a fairly major change to, even just things like career decision. It doesn't make sense to do a PhD that's going to take 5 years to complete if you think that AI is already going to happen by then. But I don't find many situations where thinking like, oh, is it 12 years or 14 years is really that decision relevant to my research direction. I think you could also to some extent just lean towards your comparative advantage and kind of trust that it's a reasonably efficient marketplace. People are thinking a lot about timelines. People are ultimately very uncertain about timelines even after having thought about it a lot. So if you're just a really great theoretical researcher, but you think that probably actually timelines are likely to be short and theoretical research won't be useful, it might still make more sense for you to do that because you definitely don't want no theoretical research to happen. Maybe you can kind of just swap places with someone who has opposite beliefs with you, but is much better at doing the work that you think would be useful. So I definitely would kind of try and do that trade as well. But if you don't feel like a strong pull towards a particular research direction, then definitely getting some opinions on timelines can be useful.
Thanks, Adam. What are your thoughts on trying to move the approaches to AI development from more difficult to align methods like scaling ML models to relatively easier to align models like probabilistic programming?
Yeah, so I think generally it can be quite path dependent how a field develops. So if you do have an opportunity to kind of push it towards an approach that seems easier to align, then I think that could be quite impactful. That said, it's sort of hard to predict how the path dependency is going to work out. And so if you don't see a kind of clear lever for how to make a particular AI paradigm more attractive or tractable to people, then I wouldn't necessarily say you should sort of seek to do that. I wouldn't say, oh, become a probabilistic programming language researcher in the hope that you'll figure out how to scale it up and make AGI using that instead, because people are already there's already a lot of people trying to make probabilistic programming languages work. But if you were in some kind of unusually high leverage position, then it could make sense. One example it's a bit controversial, but I think is a reasonable example would be part of people's justification at OpenAI's safety team for pushing out GPT-3 and so on was they thought, oh, language models are going to be easier to align than reinforcement learning approaches. I'm not sure if that was, the right thing to do. It probably did accelerate timelines quite a bit, but that definitely kind of all else being equal was an advantage. If they could choose to either, push out a really impressive language model release or push out a really impressive reinforcement learning release, it probably was the right decision to go for the language models.
Thank you. This question has been upvoted a couple of times, so it's quite a popular one. What are the threat models you envision from LLMs? Are there any evidence for emergence of agency in these models?
Yeah, so I think that contemporary language models, I don't think that GPT-3 is going to wake up one day and decide to take over the world. But definitely the objective that a language model is being trained with to just kind of imitate internet text perfectly is going to, if it were the limit of infinite data and compute, would eventually result in it being able to perfectly simulate a wide variety of humans. And humans have agency, so I think at the very least we should expect that these models, when prompted with a text that would imply some agentic planning, are going to continue to do that capably. Now, where they have their own inner objective that is sort of different, independent of a prompt, I think that's a bit harder to say. Definitely there's a possibility that at some point that just is kind of the easiest thing for a gradient descent process to learn. But I'd probably be more concerned about if you then fine-tune it with something like reinforcement learning, then you're putting more optimization pressure towards agency. But unfortunately, it just seems like we kind of need to do something like that in order to get any useful behavior out of these models. So I say we don't currently have a way of kind of safely applying optimization pressure without creating agency. In terms of kind of a concrete threat models, I think probably for the language models, I'd be most worried about deception because they're already pretty good at that. Humans are also pretty good at deception, so there's already lots of kind of training data on that. So I'd expect it to be already we probably have systems that are getting more human approval than they should be, just because they're being like very polite and courteous to people. And if we just keep on scaling that up, we're eventually going to get systems that are doing things quite different to what we wanted. But we might find it increasingly hard to tell that that's what's going on.
Thank you, Adam. About 4 more questions at the moment, so I'm going to try to go quickly. What are your thoughts on installing the notion of emotions in AI? Why can't models be trained with humanitarian emotions, and that could be correlated with tasks that the AI has an option to choosing to do or not to do by the emotions or feelings that it could have?
I think I missed some of that question, so can I just... I see. Okay. Yeah, that's an interesting question. I mean, I think that this ultimately comes down to sort of how do you make AI systems that are more human-like. So, if models generalized in a human-like way, that would be nice. If models had human-like motivation and emotions, that would be nice. I think that the main issue is I don't really think there is a natural place to insert emotions into a model. Because we ultimately we're not building these models in a modular way. We're training them end to end. So I think to some extent, if you're able to get to a point where you can say, oh, we have an emotion of a system is like cooperative and helps other people and cares about them, so like you've already solved some of a problem. But definitely there could be an interesting approach to kind of taking a more modular approach and trying to mimic a human brain, trying to mimic cognitive science theories, so that we can actually kind of reason about it in a human-like way.
There's about a couple left, but this one is quite upvoted as well. What agendas are you on FAR AI most excited about or are working on?
Sure. So I mean, to some extent, FAR AI is trying to not be too opinionated and incubate new agendas. So I sort of feel obligated to give that caveat that if I say something that you disagree with, you can still pitch us on an idea. But the things I'm personally most excited about would be looking more into this adversarial robustness angle and just trying to understand what does it mean for alignment if every system we have can be adversarial exploited in some way. I think it doesn't mean that we're doomed, but it might mean we need to have systems that are much more fault tolerant, where we just think that everything is going to be exploitable, so we have to kind of just make things either limit how much optimization pressure happens so we don't get exploited, or just have a bunch of kind of checks and balances so that it becomes very hard to consistently exploit a system, even if we can get exploited now and again. I think there's also a lot of interesting directions in mechanistic interpretability. It's a huge area, there's already a lot of people working on it, but they're mostly working on kind of a fairly narrow range of agendas. So I'm interested in kind of novel approaches to mechanistic interpretability. Someone at FAR is currently working on a tuned lens approach to understand the activations of a model in terms of predictions of an X token.
So Adam, I think lunch is going to start in about 4 minutes, and as MC, I've decided to take freedom to make you guys stay the extra 4 minutes and ask the rest of the questions, if that's okay. So someone made a comment and a question, which was, I feel like a lot of effort is made to make AI systems think more like humans, but is it a good end goal? For example, some problems nowadays in applying ML models stem from biased training data because humans have been biased and have been making discriminatory decisions themselves. So it seems to me that if the goal is to make AI as aligned with humans as possible, it will result in a feedback loop of discrimination and bad decisions. Should there be more effort in using AI as a tool to counter bias?
Yeah, so this is a really important point, that most of the data sets we have are currently very biased, both sort of explicitly, they might include sort of toxic value judgments in some cases, and also just implicitly, there are some languages that are better represented in the text than others, so we're just primarily training on kind of Western, educated, industrialized, rich, democratic, weird nation states data. I think it's worth noting that current ML systems actually kind of amplify this bias. So it's not just that the training data is biased, but actually ML systems are kind of even more biased than the training data, which is particularly problematic. I think that if you have good human feedback, then just because the internet is toxic doesn't mean that your resulting model is going to be toxic. So I think to some extent the alignment approaches people are proposing should help with this, provided we're able to get the right judges to train these systems. And that may be a challenge, but it's sort of a challenge we're used to solving. It's like the same thing of like, how do you elect a good leader, right? Well, okay, maybe we haven't solved a problem, so I don't know how much comfort we should have with that, but it is maybe a problem that's going to be hard for AI research to solve. What I would say is I think it's very important so whatever we do does not have value lock-ins. There are probably things that all of us believe right now, but in a century, people are going to look back and be like, oh my god, my grandparents believed this? This is like terrible, right? Like how we think right now, some maybe like dated beliefs. So I want to make sure whatever AI systems we have are able to ideally enable, but at least not get in the way of moral progress. So maybe we do have some issues with bias, but I want that to make sure that's at least a temporary problem, not a permanent problem that the AI locks in.
Thank you very much. After my announcement, people sent in more questions, but unfortunately, I think those would take a bit too much time to answer. There's one last one that I think you can take, which is human brain-inspired AI limited by our current computing power or limited by our models of the brain?
I'm not sure I'm the right person to answer that. So, there are things like C. elegans, which is this tiny nematode worm that has something like 100 neurons and they've been perfectly mapped out, and we still can't really simulate C. elegans correctly. So I'd say, that's something we're limited more by having like the right models. Although I think it's also a bit challenging because C. elegans doesn't have that much behavior, so you kind of people are arguing like, oh, is it wheeling in the right way or not? And that's just like a bit unsatisfying. But I do think that if we had enough compute, we could kind of make a lot of progress without having the right models of a brain, because we could do things like just optimize over this really high-dimensional parameterized space of possible models of a brain and figure out one that works. Maybe we wouldn't get something that's exactly like the brain, but we might get something that's still intelligent. So to some extent, kind of compute and insight can trade off against one another. I expect if we had the right models, we already have enough compute to simulate the brain. But it may be that we get kind of enough compute to bypass that before we figure out how the brain works.
Thank you so much, Adam. I think that would be the last question before lunch starts. And can we all put our hands together in applause and appreciation for this fantastic talk?